that was supposed to be hands-on, and the meaning of hands-on is that you do things along with us, and because this is an online course that poses some challenges, yet we were hoping this to be a more interactive experience, but unfortunately that has not happened. So in fact, we several times we encouraged you to write to us if there are specific issues, specific questions, but we haven't heard anything as yet, apart from some minor queries in the initial days. So I do not have a very clear idea as to where each one of you are and whether you have any specific difficulties that needs attention. Yeah, so that sort of puts us in a situation where we are unsure about whether we are going too fast, going too slow, if things are looking too formal to you, or you expected more of practical things. And even in that hands-on things, there are several codes, several things that I showed, and all of those require substantial amount of time investment if you want to be familiar and comfortable with those. So we don't have a feedback as to how that is going. All right. Okay, so therefore, what I decided is that we have had one such interactive session earlier. The Monday's class will be interactive, and I have already sent out a mail, and I expect at least the credit students to be present. I mean, it's mandatory for them. So again, I will pause here for a moment, and I would like to know if any one of you have gone through the basic ideas of tree-based methods, random forest in particular, and if you have any questions or any doubts that you did not understand. Today's will perhaps be a short class because I don't want to cover too much of new stuff today. So, any questions? Any thing that you want to be discussed again? Okay. In that case, what I'll do is I will just go over some of the basics that I'll quickly go over things that I already discussed in the last lecture, and then I'll show you the a code for random forest regression, and I'll leave you with a task that I'll come to at the end of my lecture. All right. So yeah, so what I said last time is that the idea of tree-based methods is that you have your samples, your training samples in your feature space. There are axes representing the features, and sequentially you divide. I mean, basically the idea is you divide your feature space into boxes, non-overlapping boxes. And the way you do it is there are several ways you can do it. I mean, the basic idea is that you choose a particular feature axis, you choose a particular value on that axis, and you draw a line from there perpendicular to that axis, and that creates new regions for you in the feature space. So these are general tree-based methods. So you divide your feature space into J distinct non-overlapping regions, and for a test sample, so when you make predictions, if a test sample falls in a particular region Ri, you predict its value to be the simple mean of the training observations in that region. Very simple idea. The regions could have any shape, but for convenience and the way these things are created, they are chosen to be high dimensional boxes, as I said, and the whole purpose is to reduce or minimize the residual sum of squares. And anytime you train a model, so basically you are trying to typically minimize something in this case, and that is called the loss function. You try to minimize your loss. Recursive binary splitting is the easiest way of creating trees, but we say they lead. I mean, recursive binary splitting leads to complex trees, typically overfits training data. One could do with smaller trees, which may not fit the training data so well, but then such smaller trees do better for test sets. And the question is, how do you prune the trees? There are ways of pruning trees, but that we did not discuss. All right. And then that was the regression model, the regression task. You minimize the residual sum of squares. The question is, what do you do for classification trees? For classification trees, you either minimize the Gini index, or you minimize the entropy. And here are the definitions. Okay, so the point was that in general, decision trees have large variance. Decision trees, we are not talking of pruning trees. Talking of general decision trees, so they tend to have large variance. That is, you change your training data and the tree changes significantly. So if you take a large training data set, split it into two halves randomly, and you train two models, they would look very different. And as a result, if you now have a test set for the same test example, the predictions from the two models could be very different. So how to reduce this variance? So we did bootstrapping. We drew n independent samples of the same size from the original data, and using this idea from statistics that if you have a certain number of independent random variables, each with a variance sigma squared, you take their average, and the variance of that average now becomes sigma squared over n. So the idea was that if we can train a large number of trees, make independent predictions from those trees, each one of those would have large variance. So the values may vary from model to model, but when you take average of such n quantities, that variance will be reduced by a factor of n, where n is the number of trees. And such simple averages taken for such over many trees is called the bagging method. So that is for, you can take a simple average for the for a regression model, but the question was, what do you do for a classification model where you do not have continuous values? It's neither this class or that class or that class. So one way is to take a majority vote. So if out of the n models, if whatever class majority of the models put a particular test sample in, you take that to be its class. So suppose there are 5 classes. So let me give you an example. Suppose you have handwritten digits and you are trying to, you have a model through which you are somehow trying to identify which digit it is. And say you have 100 models, and maybe 60 of them classify something written on a piece of paper as, say, being a 5. And there are other models, rest of the 40 models, some say 1, some say 9, etc., etc. Because 60 is the majority number, which say it is 5, you classify it as 5, and so on. There are other ways of doing it. You can calculate the probability of a sample being in various groups, and whichever comes up with the largest probability, you classify it in that. And in that case, actually, you can actually take an average of those probabilities. All right. So, what is random forest then? Random forest is a slight tweak on these decision trees or these bagging method. Um, at each step, you do not try to do a division over all possible features in your model. So if there are n features, recursive binary splitting would look at every feature and try to find out which value of which feature, if you do a division at that value, leads to the largest reduction in the residual sum of squares. Instead, what a random forest does is, at each step of the split, it considers only a certain number m of features, which is typically much less than p. If m is equal to p, you have recursive binary splitting. But in the random forest, typically m is taken as something close to square root of p. So you consider, randomly choose square root p. P is the total number of features. You choose randomly p features, I'm sorry, n features, which is square root of p, and you search that what to split along which value of these features only. The rest of the features are not even considered. And so what it does is, you create a large number of trees, but these trees are not as correlated as if you had, you know, created uh, the same number of trees, and each one of them by using this recursive binary splitting. Okay, so this is a, so we'll now try to see, sorry, yeah, what is there in random forest. Okay, so random forest has many hyperparameters which need to be optimized. So hyperparameter optimization is an important step. You have to have the right model, right structure of the model before you can train it on your um, training data. Yeah. So here are random forests. So basically, yeah. So let me see. So random forests, as I said, typically rely on deep trees which overfit individually. Deep trees are those which have many nodes and leaves, which uses much computational resources, and they require several splittings and evaluations of boosting models build shallow trees which are faster to fit and predict. Okay, so now there are these extremely randomized trees. I will go to the part where the model is defined. Random model regressor. Just give me a minute here. Yeah. So this is the part I was showing you earlier. So there are several parameters that you can pass. If you do not pass, of course, it will just take some default values. So first one you see is n estimators. So this is how the random forest regressor is defined in scikit-learn. N estimators is the number of trees. So by default, it will take it will create 100 trees. And when you make a prediction for a particular test sample, it will be the average of the predictions made by these 100 trees. Okay. Then you see criterion. How do you train your model? Squared error. That is, you are minimizing the residual sum of squared. So that is the error. So that is how minimizing that the model is trained. Now then there is something called max depth. So let us see what max depth is. So there are, you can interpret it too. So it is the maximum depth. Depth means depth of the tree. So what is depth of a tree? So let us go to. So here, okay. So how many branches you have created here? You have created two splits here. Okay. So that is the depth. The more it is, the more complex a tree would look like. So if you define a number, it will take it, which has to be an integer. If the default is none, then nodes are expanded. So you keep on splitting until all leaves are pure. That is, there is nothing else to split. There is only one sample in a particular region, or until all leaves contain less than minimum sample split samples. So you can define this parameter as well, minimum sample split, the minimum number of samples required to split an internal node. If a node, that is, if a particular region at any stage contains less than this number of samples, then it will not be considered for split anymore. Okay, so max depth and minimum sample split together define how the tree is structured. So you already saw that. Minimum samples leaf. So let us go down slowly. Minimum leaf nodes. This grows trees with maximum leaf nodes. So how many maximum leaf nodes you can have? Okay, leaf nodes is where you don't split it anymore. Bootstrap, whether you do bootstrapping or not, it's a Boolean thing, true or false. Out of this OB, I mean, I have not discussed. Njobs is about how you run it. Random state is the seed for random generation, random number generation. CCP alpha is related to tree pruning. Typically, you don't need to do it. Max samples is related to the bootstrapping process. If bootstrapping is true, which is the case for random forests, the number of samples to draw from your samples to train each Bayes estimator. Okay? How many samples? It all could be of size n, where n is your training set data, or it could be smaller than n as well. Okay. Let's see which ones. Let me now go to a code that I have, and sorry, this has to be here. Yeah. So the first few lines are as usual: matplotlib, seaborn, numpy, statistics. Here is the important line. Random forest regressor. We are doing regression using random forest. The next line, line 7, are the matrix that we use to this we have seen before. Next line, cross validation, grid search CV. This will be more important for a random forest model, uh, uh, particularly a grid search CV, and I'll go to that part of the code in a while. Pre-processing we have seen. Transformers we have seen. Okay. This, just ignore this for the moment. The syntax may not be absolutely correct, but here is the important part. I have a CSV file containing my data. It's the same data that we used earlier. Then usual. So I read in the data as pandas data frame. Then uh, we have to, of course, import train test split. We choose the column which contains my target values. In this case, the eta formation or formation energy. We drop the columns that contain data that we do not want in the features. All right. And then the usual things, we define the transformer, we do the transformation on the training set features and the test set features. Then Y train, these are reshaped. Then we define the transformer for the target data. Then the test and the training set target features, target values are transformed. So this part is just data pre-processing. Then here comes the important part of random forest. I have not defined all the hyperparameters. Some I just left as default values. Some I have defined here. Things that I was showing you earlier. So depth is the maximum tree depth. So we are trying all sorts of values from 2 to 20, 19 different values. Minimum split, that is what is the minimum number of samples a particular region need to have for it to be considered for a split. So that again is varied between 2 and 10, 9 different values. Maximum sample, maximum features, this is very important. Max features is that value of m, the quantity m, the number of features that are considered for split at any particular step of tree creation. And square root here means that m is equal to square root of p, or the nearest integer. And alphas, as I said, is related to tree pruning. I have some values here, but you can ignore it. So when I share this script, you can in fact comment those lines. So the parameters, so these define ranges of values for each one of these. And then the parameters which will be passed on as a parameter when I do grid search CV for my model is defined based on these lines above it. So max depth is depth, and depth is this. So max depth will vary between 2 and 20. max samples will vary between 2 and 10, and sorry, the minimum split will vary between 2 and 10. Max samples is set as 0.6. That is the 60% of the total samples, and CCP alphas. If you do not use it, you can comment this particular line then. Okay. Now, here is the hyperparameter optimization line. So I'm trying to define a random forest. What is that random forest model? We have to find the correct model, the correct hyperparameters, the correct values, the optimal values of all these quantities by using doing cross validation using grid search. So I have defined a grid already. So the cross validation score will be calculated at all possible values of the grid. So I have 19 values for max depth. I have 9 values for mean sample split. I have 1 value for max samples. I have 1 value for max features. So all these things, all possible combinations of these will be taken. And for each combination of these parameters, which is like 1 point, each combination is 1 point in the hyperparameter space, this cross validation score will be calculated, and whichever set of values gives the lowest cross validation score will be used for the model training. Okay, so this line optimizes the hyperparameters and finds the model form. So grid search CV for a random forest regressor, criterion equal to absolute error. It is trying to optimize the absolute error, not the square of error. Max features, I have, I think I have repeated it here. No, max features is given separately. So this is square root, means m is equal to square root of p. Parameters is this range of parameters that are defined here. In jobs equal to minus, this is about parallelization. CV equal to 5 means I'm doing a 5-fold cross validation. So my training set is divided into 5 folds. 5 cross validation scores are calculated each time. Sorry, 5 mean absolute errors are calculated, and their average is taken as the cross validation score. So I get 1 cross validation score for each combination of features, hyperparameters, and then I take the condition, the set that gives me the lowest cross validation score, and that set is used. So that defines my model. Once I find my optimal hyperparameters, then I define a model opt, which is rf.fit x trained scaled, the scaled training set features, and y trained scaled, that is the scaled output values. So this is the line where the model is actually getting fitted on my training data. The previous line defines my RF model, the optimal set of hyperparameters, and this highlighted line actually fits the model parameters with the training data. Now, there are some models, not all models, in which you can figure out or you can determine which are the features. If you have many features, which are the features which are playing the dominant role in determining the output, the target value. Of course, the linear regression is, or any variant of linear regression is one of those, whether lasso or ridge regression, because whichever is the largest W, after you have scaled your features, whichever is the largest W is the one that has the maximum effect on the output. Similarly, in random forest, it's the feature which leads to maximum reduction in RSS is, or gets selected for splitting the maximum number of times has an important effect on the target value, and you can rank them according to this importance. So this is feature importance, which sometimes provide important insight into how different features are uh, playing role in determining the target. When it comes to materials issues, you must remember that whatever feature importance you get, whether in a linear model or a random forest model, is not, it may be related to physics, it may not be related to physics, or your. So when I say physics, what I mean is that there may be a causal relation between a particular feature and the target value, which from the physics principles is sort of obvious to us, known to us, and the model just reinforces that. Our model finds the same thing, that this quantity determines the output. Sometimes some features come out with importance, high importance, of which you cannot make an immediate meaning based on your knowledge of physics or chemistry of materials that you have. So in those cases, probably it's just a correlation given your training data. That's the correlation between the feature and the target property. Whether there is truly a causal relation between the feature and the target property is not so obvious. Okay, so we can print out the importance, and then we can also print out what are the best optimal parameters that the model found, the R2 score, and uh, R2 score for the training set, the test set, usual things that explain variance, which gives me an idea about the performance of the model. Okay, so these are things we wrote for the linear models as well. So as it turns out, linear models are absolutely quick to train, at least for the number of data points that we have in this data file. So I could run and show you that model on the screen. In fact, I have the results here. So these results at the bottom. So this is, I think, which one did I run? Lasso, I believe. Yeah, one of the linear models. This is probably Lasso. So you see the test set mean absolute error is 0.33. The root mean squared error for the test set is 0.41 EV per atom. And the R2 square for test set is really small. Now, random forest takes considerably longer to train, and it is sort of not possible for me to run it and show you live. But what I have done is I ran an instance of it on the same data. Okay, on the same data, I ran it, and I have the results here. Uh, there isn't much to understand from these features, because all these features, they don't have any direct physical meaning. Remember, we were using the sign matrix eigenvalues as our feature. This is more to show you how to run these codes rather than um, developing physics insights into this. Uh, but you remember, and I will show you once again, if I can show you the data file. um, so the eigenvalues are ordered in increasing values. So as you go to this later eigenvalues, for a given material, they are larger. So in general, eigenvalues that are in the range 21 to serial number 21 to 30, they are larger in number compared to the earlier ones, which are largely zero. Okay, this is just because the way we have arranged them. So obviously, features that are small in for most of the materials, they are zero. So they don't determine very much on an average. So you see, these earlier features are lower in rank, whereas the later features, so eigenvalue number, whatever this is, 28 or 29, these are higher in importance. So there is no surprise there. There's nothing much to be understood from here. Here are the base parameters that the hyperparameter optimization through grid search cross validation produced. So the maximum depth of the tree was found to be 20. 20 was the maximum allowed value. So in that sense, I probably should run it once more, try larger values of the optimum parameters. Maximum samples, that it was fixed at zero 0.6, minimum sample split. This, you see, the model has come up with the optimum value of 3. So there should be at least 3 training samples in a region for it to be considered for a split. Okay, now here are the results for the original data after we have done the inverse scaling. So the mean absolute error for the training set and the test set, I'll try to show you both of these together. See, these are the numbers. The training set value is 0.09 and the test set value is 0.15. And these values are much smaller than these values for the linear model, which is 0.322 and 0.33. So obviously, this model is performing much better than the linear models, which I said was expected. However, I see still a bit of a problem here because the training set in mean absolute error is much smaller compared to the test set error. So the test set error is much larger. So I suspect there is a bit of overfitting happening here. So one might be able to get better results by tuning the hyperparameters even further. These are the same things rather than mean absolute error. These are the root mean squared error, the training set and the test set. Forget about that line. This line, do I have the R2 score somewhere? Should. But the R2 score I have for the unscaled data, that is data before scaling it back to the original units, and that R2 score is 0.76. The comparable thing in the linear model, I'll just go back there, was 0.25. So 0.25 versus 0.76, that's the kind of improvement you see in a random forest model compared to a linear model. Linear model is a linear model that has that bias. You cannot avoid that. Whereas random forest doesn't have a particular functional form. So if you put enough effort to sort of optimizing your hyperparameters, it's only likely, because it should be better able to represent nonlinear functions, you expect to get better results. And the relation between the heater formation and the sign matrix eigenvalues, if anything, would be very nonlinear. There is no reason for them to have a linear relation. So these are the things that I wanted to show you. So now you have some idea that how random forest does better than better than the linear models. So with that, I don't have anything new to show you today any further. What I'll do is I will share this random forest script that we were seeing here, and I will specify the tasks with you. I will send it over email. I ask you to optimize some of these parameters. I'll specify which ones you should optimize using grid search CV, and you should run it on the same data set and see what you get. And I will also give you a task where you try to use it for another a different regression task. Okay, so these are the two tasks I'll give to you, and hopefully I will get to hear something from you on Monday. Okay, so I'll share these very soon on the page. So that's all the new things I have for today. If you have any questions, you can ask me. Okay, if not, we'll close it today, and we'll meet on Monday, and I will ask you about your progress.